You may have heard of something called the Intermediate Value Theorem, which says if you have a function that obtains two different values and that function is continuous, then it has to take on every intermediate value. So in the context of this picture here, our blue graph has to cross that purple line at some point. And so if this is a graph of y equals f of x, then the answer is definitely yes if the function is continuous. But there's actually another case where it's true, where we don't actually require continuity. And that's the case where we have the graph of a derivative of some function. Now, the derivative of a function doesn't necessarily need to be continuous. It can kind of have some crazy behavior. But as long as it's the derivative of something, we're guaranteed that that graph does have to cross this purple line. And I'm going to go through a proof in this video. Now, the first thing you might think to do is just to subtract m from all the sides, and that would definitely give you a 0 in the middle. And that's a great start. But to really apply what we have in our statement, we have the derivative of something and the derivative of the same thing but evaluated at a different point. So we really kind of want one function there. And so we're trying to ideally end up with some function, maybe p of x, so that p prime of a is our small value, p prime of b is our big value. And pause the video to try to think about it, but I bet you can come up with what a function p of x would be that would do this. What did you get? The one that I picked was letting p of x be f of x minus m times x. I notice that if I use that property there and I take the derivative, well, p prime evaluated at a is just going to be f prime of a minus m, right? Because the derivative of mx is just going to be m. And so this function here is going to give me the thing that I wanted, where 0 is now in the middle. And so now we're ready to move on to idea 2. I've gone ahead and shifted everything so that intermediate value is now 0. And we have our 2 points. We have that p prime of a is a negative number, and p prime of b, maybe I'll put that up here at the top, p prime of b is actually a positive number. And so we're trying to show that the function has to cross this middle line, which is equivalent to showing that there's some input that we plug in that gives us exactly 0. And the next big idea is to think about extreme values. Now let me talk about what I mean. We're going to shift our focus now and think about the function p of x itself. So remember, p of x is just f of x minus m times x. We're assuming that f is a differentiable function. It has derivative f prime. So p of x is definitely a differentiable function. So we're going to record that now and use that in what follows. So what do we have? We have a function p of x that's differentiable, and it's continuous. It's got lots of properties too, but it has to achieve a minimum somewhere on the interval from a to b. Actually, every continuous function on a closed interval has to have that minimum. And there's something called the extreme value theorem that says that that minimum has to either happen at an endpoint or at some critical point, some point where the derivative is either undefined or equal to 0. For instance, here's a function that achieves its minimum at a critical point, a point where the derivative is 0. Here's another example of a function that's not differentiable but still does achieve its minimum at some critical point where the derivative is not defined. Finally, here's an example where it achieves its minimum at an endpoint. So what do we know about our function? Well, we know it's a differentiable function. And so if we know that the minimum has to happen at a critical point, then that would force the derivative to be 0, because it has to be defined. And so critical point therefore would mean that the derivative exists and is 0. And so now this kind of points us to a goal, which is if we can eliminate this option, if we can eliminate the possibility that the function p of x has a minimum at one of the endpoints, a or b, then that would mean that the derivative has to be 0 somewhere. And oh my gosh, that's exactly what we're trying to show. So let's do that. And this is maybe my favorite part. So what do we know? We know that we have a function, and when we take the derivative at a, we get a negative number. And when we take the derivative at b, we get a positive number. So this orange function here is going to be a graph of p of x. And so now this negative value, that's actually saying that this slope is negative. And this positive value over here is saying that that slope is positive. And now I think we're there, because remember our goal. Our goal is to show that the minimum of this function does not happen at a, doesn't happen at b, it doesn't happen at the endpoints. And you can kind of see that, like, of course the minimum can't be there because there's like lower values just to the right of it. And the minimum can't happen here because there's smaller values just to the left of it. And if you want to see how to make this rigorous, well, just think about what the derivative would mean, right? This thing here is the derivative of p at the point A, and we know that that's supposed to be a negative number. And so that must mean we could plug in values, to the left or to the right, or in the context of this, it would be a positive or negative h values. That must mean that there's some tiny bit we can move to the right and get that numerator to actually be a negative number so that that fraction were negative. And so that's kind of what I've written down at the bottom. But basically, this shows us that there's some point just a little bit to the right of A that's going to have a smaller value. And similarly, we can do the same thing over here to get some small, I guess we have to also say that h is positive, but some value to the left of B that's going to be a little bit smaller. And so all of this kind of put together, what that shows is that we cannot have our minimum happen at one of those endpoints. And since we've reached our goal by that extreme value theorem, the minimum, which has to exist, must happen at a critical point. And since our function was differentiable, that critical point has to be a point where the derivative exists and is equal to 0. And that's our goal. So that's how you would unravel everything together. I'm not going to write the whole proof here because really this is about the ideas. But if you want to take a crack at writing all the details down and maybe make a reply video or send me an email, I'd be happy to take a look at it. Thank you so much for watching. And if you value this content, consider hitting subscribe or leaving a comment about what you liked about this video and what else I can do on this channel. Thank you so much.